We are working on homework 2.5, equations of motion, and this is going to be question number 4. Homework 2.5, number 4. And 4 is broken down into A and to B, and I'll write separate sections for that, but for now let's just write down our givens. So a rocket blasts off and moves straight upwards. Now, before we even look at any numbers, a rocket blasts off. Okay, what is the initial velocity? Well, rockets usually don't get a moving start. They're usually stationary. We're going to assume this rocket is also the same, so our initial velocity, VI, is 0 meters per second, even though we weren't initially told that. And it moves straight upwards with a constant acceleration. That simply means that all 5 of our equation derivations are they're good to go. Our acceleration rate does not change. We have delta t equals 3 seconds. Oops, that looks like 35. Our change in time is 3 seconds, and it has gone a displacement or a distance of 77 meters. So the question is, for A, right here, what is the magnitude of the rocket's acceleration? So A is what we don't know. Well, are there any equations that relate just the initial velocity, the time, and the displacement to A? And there is. I'll write it down here. There's our equation number 4, which is displacement is initial velocity times time plus 1/2 times acceleration times time squared. Well, again, we want to solve for acceleration, so let's start moving some of these values around. We're going to subtract VI times time from both sides, so delta x minus VI times t is equal to 1/2 times A times t squared. So I just moved this over to that side. And I'm going to divide by t squared on both sides. T squared, and multiply by 2 on both sides to get rid of that 2 in the denominator. So 2 and 2 over here. So our final equation for A is 2 times delta x minus VI times t over t squared is equal to our acceleration A. So before I use up too much of B's space, which is right down here, I'm going to move up to the top right here where we have a little more room. So let's put in our values. So acceleration equals 2 times our displacement, that is 77 meters, minus our initial velocity, 0, sorry about that, 0 meters per second times t, so 0 meters per second times our time t, 3 seconds, 3s. Don't forget your units. I forget sometimes too. All that over our time squared, so 3 seconds squared. So our acceleration at time equals 3 seconds, if we calculate that out, should come out to be 17.1 meters per second, or meters per second squared. That's A. Now, part B asks us, what is the speed at this time? Or since our rocket is moving in a straight line, you could also say, what's the velocity? And that would be fine too. So our VF, because we know our VI, our VF is what we do not know. Everything else by this time we do know. So what equation would we use for this? Well, our first equation, our first derived equation, should work nicely. We have our initial velocity, we have time, we have x. Actually, we could use a number of equations, but I'm going to use our first one, which is VF, that is our final velocity, is equal to initial velocity plus acceleration times time. Because now we know the acceleration, we knew the time, we already knew the initial velocity, so now we can solve for v sub f. So that equals 0 meters per second plus acceleration, which is 17.1 meters per second squared, times time, which is 3 seconds. That'll give us an answer in meters per second because this second and this second squared will cancel out, and we get an answer of 51.3 meters per second. Oh, you know what? I should just rewrite that with what I'm solving it for. That's velocity F, final velocity, equals 51.3 meters per second.